All right, good evening, everyone. My name is Bob Lemieux. I'm Dean of Faculty of Science at University of Waterloo, and it's my pleasure to welcome you to the Bridges Lecture Series, which is, of course, as you know, a series of lectures that connects art, science, and mathematics. Tonight's lecture is the first of our 9th season of the Bridges Lecture Series. And I know that we're going to have another really interesting year with some very colorful and interesting lectures in this series. Before we get started, I want to make sure that we thank our sponsors from the University of Waterloo, the Faculty of Arts, the Faculty of Mathematics, and the Faculty of Science, and also our host and partners at St. Jerome's University. This collaboration has been going on for many years, as you know, and it's been a very good one. It has allowed us to attract some absolutely world-class speakers to this series, and tonight there's certainly no exception. Tonight we're going to be talking about the glass problem, changing and challenging material definitions. And we have, as I said, two outstanding speakers tonight. They will speak back to back. The first speaker is Katherine Larsen. Katherine is curator of ancient and Islamic glass at the Corning Museum of Glass. Kate's research focuses on ancient glass technologies and changing practices of glass production and consumption over time. She serves as a glass specialist for archaeological excavations in Israel, Greece, and Turkey. She holds a PhD in classical art and archaeology from the University of Michigan. And our second speaker will be Patrick Charbonneau. He received a PhD in chemical physics from Harvard, and he was then a Marie Curie postdoctoral fellow at the FOM Institute Amalf in Amsterdam. And then he joined Duke University in 2008, where he's currently associate professor of chemistry and physics. He's an expert in numerical simulation and theory. He studies the assembly of various colloidal and molecular systems, including protein aggregation, as well as the glass problem. And so, without further ado, please join me in welcoming our speakers, and Katherine will be beginning.
Good evening, everyone. I'd like to start by thanking the organizers for putting together what I'm hoping will be a really stimulating series of papers. I've already learned a lot and started thinking about my own research in new and different ways, which I'm hoping will kind of come out over the course of this lecture. So, as stated in the introduction, I identify as a historian and an archaeologist and an art historian and a curator. But I'm not a philologist, although there is a good amount of philological language-y discussion in my talk tonight. So I apologize that I'm skating on the edges of my familiarity. But I think I'll draw it all together, and I think this is really what the Bridges series allows us to do, is kind of think about some of these issues and problems in new and interesting ways. So. As Patrick started to tell me about what the glass problem is in his discipline, as I understood it, it was basically a definitional one about the state of matter glass occupies as it moves from a solid to a liquid. Is that? We'll learn more about that later. But it really made me wonder anew how people in the ancient world thought about glass. How did they define glass? And most of us today, even we're familiar with, we've used microscopes, we study atoms and molecules in high school chemistry, but we still aren't used to thinking about material at an atomic scale. So the more I thought about what a meaningful definition of glass might be in the ancient world, the more slippery that definition started to feel. It was based either on this kind of scientific definition that we're still struggling with today, which has no real ancient relevance, or physical properties of what turns out to be a really mutable material. So here's an example. In the 1980s, the landmark museum exhibition Glass of the Caesars showcased 150 stunning and remarkable glass objects from the Roman world. But there turned out to be one problem. The cover image, this lovely head of Augustus on the cover of the catalog, turned out not to be glass. Shortly before the exhibition opened, scientific analysis conducted on this object established that this glass head, in fact, has a crystalline structure and not the diagnostic non-crystalline structure of a true glass. I'm sure we'll hear a little bit more about this. But, all right, so with the help of science, we therefore learned that this glass object isn't actually glass. But to me, this discovery invites a more interesting question, which is much harder to answer, and that is, would a person in the ancient world have considered this object glass? Of course, a Roman, or Michael Palin as our proxy, would not know glass as a word or concept. Glass is an Old English word with Germanic roots, which first appears around the 9th century. Instead, our hypothetical Roman would ask, is it vitrum? The Latin word vitrum, it seems to map reasonably closely onto our modern English concept of glass. So we assume, therefore, that each of these glass objects from the Roman world, different as they are in color, opacity, decoration, and manufacturing technique, would all have been considered vitrum. But the history of glass is a long one, predating Romans by thousands of years. The earliest man-made glasses date to the second half of the 3rd millennium BCE. And I'm entirely leaving aside here the long history of human use of naturally occurring glasses like obsidian. So fewer than 24 pieces of true glass date to this early period. The most charismatic among them is this small chunk of raw glass, which was found at Eridu in Iraq and is now in the British Museum. And this slide makes it look much better than it really is. It's actually, a centimeter big. It's teeny tiny. These early glasses are probably accidents or failures produced by mistake during the manufacture of ceramic, glazed wares, or faience. Faience is a material made from similar raw ingredients to glass, but it's worked in the form of a paste, so it's got a little bit different properties. In the 16th century BCE, there was a sudden proliferation of glass objects, which we recognize as the birth of the glass industry. An explosion of glass objects occurs essentially within a generation in Egypt, northern Syria, and Turkey. And as you can imagine, this makes it very difficult for archaeologists to pinpoint the place and origin and time of this nascent industry. So on screen are two of the early candidates right now for the earliest glass found that are products of this industry, and they're both found at a Hittite site in Turkey. So based on these find spots of where we're finding ancient glass, the earliest glass was closely connected to royal palaces, which may have held a monopoly on this new material. One of the earliest indicators of this connection comes from the Hall of Annals at Karnak in Egypt. A narrative relief on the wall of this temple shows the pharaoh Thutmose III offering objects to the god Amun. A set of circles, which you see here, that have traces of blue paint still partially visible on them. And they're labeled Menkaper, lapis lazuli, and Menkaper, turquoise or malachite. Menkaper is the throne name of Thutmose III, so the substance he's describing must be important enough, significant enough to carry the name of the pharaoh himself. The round shape of these objects, however, suggests that they're not mined stone, as the name lapis or turquoise might imply, but rather they're probably glass ingots. Archaeologists have found Archaeologists have found similar glass ingots at the Egyptian royal city of Amarna and in the Uluburun shipwreck located off the southern coast of Turkey. And this demonstrates an international trade in raw glass at this point in time. It was not just Thutmose III who described glass in relationship to semi-precious blue stones. Surviving late Bronze and Iron Age texts from several cultures and linguistics groups spanning a period of 1,000 years also describe glass based on this perceived relationship. In Egypt, the most common term associated with glass is jinnarwad, and it's been roughly translated as stone of the kind that flows. The mainstays of Egyptian glass production were molded and cast inlays of the type you see in the face and profile, and perfume vessels which were assembled on a solid core. And what's really interesting, especially about these core-formed vessels, is that glassworkers seem to have really embraced this flow property of glass when it's in its hot state. You see that combed decoration on the surface of the glass, which can only happen when the glass is hot. So they seem to have really preserved this moment for eternity. In Mesopotamia, the word uknu is a generic word meaning blue stone, and specifically lapis lazuli. Most uknu was mined in Afghanistan, and the more complete term, uknu sati, means lapis lazuli from the mountain. But another term also appears in these texts. Uknu kuri literally translates as lapis lazuli from the kiln. Scholars have interpreted this phrase as a reference to glass. Similarly, a greenstone, zaganduru, may also refer both to mineral turquoise and to glass. As in Egypt, Mesopotamian glasses in the late Bronze Age tend to be opaque or translucent blue and were primarily cast in open molds. And that's why this is the same object you're seeing up here twice. There we go. So this would have been originally a really vivid blue color, and it now appears this kind of dusty way due to a weathering. We call it weathering. It's when the chemical surface of the glass changes due to being buried. So you can see the original vivid blue color of that object when you hold it up to the light. But the point here is that we see a strong correlation between the color of glass and the color of stone in these texts. In Mycenaean Greece, linear bead tablets found in palaces describe a material known as kuwano that was used for inlays in chairs and footstools. The root word also has a crafting designation meaning maker of, similar to what we saw in the cuneiform text, which again clearly indicates glassworking, probably of ingots imported from Egypt like those that I showed you earlier. Several hundred years later, the etymologically linked adjective kuanos appears in the Homeric epics of the Iliad and the Odyssey. Kuanos means something dark blue or black and shiny, such as a furniture inlay, a shield motif, an ominous cloud, the hair of Poseidon, or the beard of Odysseus. Finally, literary texts during the classical age of Greece, during the 4th and 5th centuries BCE, describe glass as lithos kaite, which means molten stone. Nor was the relationship between glass and stone limited to the Mediterranean and Middle Eastern civilizations. Ancient Chinese texts use the root character for jade, which is yu, which primarily means beautiful stone, but it also appears in the word for glass, recording in texts that span over almost 2,000 years from the Han Dynasty through the Qing Dynasty. And my colleague at Corning, Shelley Tsue, gave me this information, so I thank her for it. So, as in civilizations to the west, ancient Chinese glass was also closely related aesthetically and functionally to stone, although in this case, instead of lapis, they're looking to jade for their inspiration. So Han Dynasty tomb fittings made from glass, such as this bead disc, are often difficult to distinguish from the more common jade counterparts. So you're seeing two objects here, one made of jade and one made of glass, that are essentially indistinguishable to us. And in fact, we think that the same craftsmen were probably carving decorations on the surface of both. So why were glass and stone linked across cultures in the ancient mind? One reason must be physical. Glass, like stone, is hard, but it can be cut, ground, and polished with a remarkable level of detail. Early glasses are also mostly opaque, and their colors mimic those of semi-precious stones, although it's worth pointing out that this was also an intentional choice on behalf of the glass makers. They could have made glass look like anything, and they chose to make it look like stone, or specifically these kinds of stones. Glass and other materials were also luminous, with a reflective shine not found in unglazed ceramic and mud brick and other kind of more common pedestrian materials, which were common at that point in time. Second, scientific analysis suggests that the earliest glasses were made from quartz pebbles, which were ground up and combined with ash from halophytic salt-tolerant plants. Quartz is a nearly pure silica source, which lacks contaminants, and so with the addition of that plant ash as a fluxing agent to lower the melting temperature of silica, it quite literally became a way to transform that hard stone quartz into a stone that poured. By the middle of the first millennium BCE, a profound shift was underway in the properties and aesthetics of glass. Glassmakers in Assyria began to add antimony to their glass batches in order to produce a transparent, colorless glass which more closely resembled rock crystal. So paradoxically, by this point in time, glassmakers had begun to use a silica-rich sand, replacing the quartz pebbles. So they're no longer using that quartz, but they're making glass that looks more like quartz. The use of sand also introduced these iron impurities, which gave glass this distinctive green or blue tinge, which you still see in glass today. If you look at the edge-on of a window or other kind of thick glass object, you'll notice that kind of greenish, bluish tinge. That's from the iron in the sand that they're using to make the glass. We think of glass as clear, but it takes a lot of work to make a truly clear, colorless glass. But they're figuring it out, even at this point in time, 2,500 years ago. Nearby in 5th century Greece, the word hyalos also starts to enter the literary vocabulary. Based on the context, hyalos must refer to a transparent material, such as seen in these two quotes from the Greek playwright Aristophanes. Transparent glass was all but unknown for vessels in 5th century Athens, but was used as glittering inlays on chryselephantine statues in Greek temples. Unlike earlier words which refer to glass, in which the identification as glass seems to be secondary to the primary reference to stone, hyalos seems more often to refer to glass and then secondarily gets applied to stones like rock crystal. However, the other important thing here is that the kind of defining characteristics of glass have shifted from that opaque, blue, and molten or pourable state to transparent, colorless, and hard. In the late 4th century BCE, the conquest of Alexander the Great helped spread Greek cultural practices to the traditional glassmaking regions of Mesopotamia and Egypt. Alexander's army looted the imperial Persian treasury, suddenly releasing a vast flow of economic wealth into the ancient system. The ensuing Hellenistic period saw the rise of a stable trade in the Mediterranean and an entrepreneurial middle class with a strong desire to outcompete each other in displays of wealth and status. It was a period of both tradition and experimentation in glass, with core-form vessels such as the one you see at the lower left. This is a pretty familiar object to us by now. It's been made for almost 1,500 years, appearing alongside a new style of drinking vessel with elaborate polychrome and gilded material gracing the tables of the wealthy. But not to be outdone, the urban merchants and rural landowners mimicked these elaborate styles for their own tables by creating plainer drinking wares, such as the one at the plain monochrome glass you see at the lower right, which were made from this newly exciting and available material of glass. By the turn of the millennium, the Nile Delta and Syro-Palestinian coast had become the most important region for the manufacture of raw glass. The Belus River, which is a small stream north of Haifa, was an important source of glass-making sand, according to the written Roman sources. Numerous glass workshops dating to the 1st millennium CE have been found in this region. And in Egypt, evaporitic lakebed deposits at the eponymous Wadi Natrun in the Nile Delta were a key source for natron, which had replaced that plant ash as the source for the fluxing agent for glass, around the same time that that sand replaced quartz. The glass industry was also aided in this period by a booming maritime trade across the Mediterranean. The emergent Roman Empire connected producers to customers in markets as far afield as Spain, Britain, and even India and China. At one of these workshops, in the middle of the 1st century BCE, glassworkers began to experiment with shaping glass using breath and air, a process which would come to be known as glassblowing and change glass manufacture forever. A pile of workshop debris excavated in Jerusalem indicates this is the earliest evidence of glassblowing anywhere in the world. And as an archaeologist, the fact that the earliest evidence of something actually comes from a workshop context is extraordinary. It's really remarkable. I can't think of another example it occurs in. But what this means is that we can see from the material, we can watch these ancient glassmakers learning how to blow glass. They're figuring it out. Nobody's done this before. They're learning as they go. They're figuring it out. They're working on it. So the waste includes this collapsed bottle you see here, partially inflated bubbles, and asymmetrical rims. It's also clear from this waste that the core business of this workshop was beads, inlays, and sagged bowls of the type, that brown bowl type that I showed you a few slides ago. It's not blown glass. So blown glass is not really what they're making their money on. They're making their money on these more traditional products. Blown glass isn't yet a stable standalone industry. So around the same time as these Jerusalem glassblowers are figuring out how glassblowing works, the Roman orator Cicero was delivering an invective speech on the floor of the Roman Senate and inscribing the word vitrum into the Latin language. This is the earliest occurrence we have of this word. Cicero described the wealthy ships of his rival as they departed from Alexandria and, quote, laden with showy and colorful articles of paper, linen, and glass. So unlike Hyalos, Kawano, Uknukuri, Jinnernawad, Yu, and every other word that I've talked about so far that's preserved in ancient texts, vitrum only seems to ever refer to the material we call glass. This means that Roman, or in this case more precisely Latin speakers, seem to have shared the same cognitive signifiers for glass that we have today. Therefore, the revolution in glass, which occurred during the 1st century BCE, was not just a technological revolution of glassblowing, but also a semantic innovation in language and therefore perception of the material itself. I suggest that these two things occurred concurrently, not by a coincidence or an accident or even a causal relationship, but generally as the result of the increased presence of glass in daily life. So thanks to those kind of aspirational merchants in the Hellenistic world who wanted to set their tables with glass, glass had entered the mainstream as a commodity and was no longer the exclusive purview of that top 1%. Glass itself, like the word for glass, expanded dramatically at the turn of the Common Era. Glassblowing and its associated innovations helped introduce a new range of possibilities in glass. Teardrop-shaped blown perfume vessels rapidly replaced those core-form vessels which we've come to know and love. Blowing glass into a mold enabled decorative and even figural scenes to be reproduced in glass relatively quickly, and mold blowing also helped shapes and sizes for selling and shipping, standardized shapes and sizes for shipping commodities. Improvements in heating and annealing, as well as the thinner walls of blown glass vessels, allowed larger pieces to be made more consistently. Glass also entered the artistic sphere in the still life scenes painted on the walls of houses at Pompeii, which were destroyed by Vesuvius in 79 CE. So I hope you can see here that these fresco artists were especially playing with the opposing properties of glass as both a transparent and a reflective material. And they're taking great care to show the interior contents of the vessel, as well as that glimmering surface of the glass itself. So they're really embracing the properties of glass at this point in time. We also have textual evidence that describes from the Roman author Seneca, who stated that fruits are much larger when seen through glass. So they're also recognizing the magnifying properties of glass. Nor was this explosion in glass innovation and fascination with transparency limited to glass containers. Glass also began to be used for windows at this point in time, as evidenced by glass window panes found at Pompeii and other cities destroyed by Vesuvius. People also began to recycle glass around this time. We have texts that describe peddlers collecting broken pieces of raw glass for recycling, and scientific analysis has identified trace elements that we can actually trace where these batches are how they're getting recycled. Therefore, we can perhaps date the modern phenomenological concept of glass, along with the origins of glassblowing, to the beginning of the Roman period. Like us, people in the Roman world recognized glass as a distinct category of material with essential and unique properties, rather than a subcategory or a type of stone. They embraced the honey-like consistency of hot glass, which enables it to be inflated and shaped. Glass blowing really still remains the most identifiable and unique property of glass. And this iconic image of the glassblower persists through time, as demonstrated by the 3 images on this slide, which are 2,000 years removed from each other and thousands of miles. Romans considered glass to be a material unto itself, notable for its aesthetic properties as transparent and reflective. Rather than using glass to emulate or replace other materials, they're embracing these unique things that glass does that no other material can do. They're using it in architecture, they're using it in their table settings, and they're collecting it for recycling. So for my final bit of time as kind of a coda to this, I'm going to jump forward in time about 1,500 years. During the Renaissance, Venetian glassmakers made high-quality, colorless glass, which was known as cristallo. And again, this might sound a little familiar to you, this continued linguistic and aesthetic connection between glass and rock crystal. The secret to Venetian glass composition turns out to be imported plant ash from Syro-Palestine, that very same flux that we saw used by the earliest glassmakers 3,000 years before this. A major breakthrough in glass chemistry was the introduction of lead to the glass batch in the 17th century. This invention was long credited to the English glassmaker George Ravenscroft, although new research has indicated that glassmakers were experimenting with use of lead in leaded glass for several decades before this. Ravenscroft's formula, and we know this from his patent that he filed, specifically claimed to produce glass, quote, resembling rock crystal. High-quality leaded glass was also critical to the development of instrumentation at the heart of the scientific revolution. Optical quality glass was a necessary component in most of the major instrumentation that made the scientific revolution possible. In the telescope, the microscope, barometer, thermometer, vacuum or air pump, and eventually the light bulb, not to mention the eyeglass lenses that many of us I see many of you looking at the screen with now. These instruments required high-quality glass with its properties of clarity, transparency, heat resistance, reflectivity, and magnification. The use of glass in science also helped further the science of glass. In the late 19th and 20th centuries, chemists, material scientists, and engineers continued to experiment with the malleable properties of glass by modifying glass recipes for particular functions. Innovations such as borosilicate glass, best known by the brand name Pyrex, increased heat resistance and minimized thermal shock. Other proprietary glass formulas were developed by industry to maximize the various characteristics of glass. So, for instance, optical fiber takes advantage of the flexibility and information transferring capabilities of the material, and the Gorilla Glass that we all carry in our pockets every day is extremely strong, lightweight, sensitive. The conflation of glass and stone, in fact, actually continues in our language today. I can't tell you how many times at the museum I've been asked what the difference is between glass and crystal. The deep irony is that glass has now become so common and crystal so uncommon that crystal has now come to refer to a glass product, even though it originally referred to a stone. Just as perhaps that Greek term hyalos once meant crystal and then came to mean glass, and the Egyptians and the Akkadians and all those other ancient people that I've talked about used the same words with some modification for both lapis and glass. So I guess I would sum up by saying perhaps our semantic categories aren't as far removed from the origins of glass 3.5 millennia ago as it first appears. Glass does indeed continue to resist our firm categorical definitions in multiple contexts, in the historical and the contemporary, the aesthetic and the chemical, and the humanistic and the scientific. With that, I'll turn it over. Thanks.
So I'll try to fill up the rest of the time with a slightly different perspective on the glass problem. Right? In a sense, we've seen how the glass problem has meant already many different things for people through the ages, for the Romans, for the Akkadians before them, for the Venetians. And the glass problem was always related to some material property, right? Trying to make it more malleable, to manage to blow it, to manage to make it transparent enough, and then to eventually make scientific instruments of very high precisions that allow us now to study glasses, interestingly enough. And a lot of this tension comes from, a lot of these possibilities come from the fact that glasses are really unique materials. And the uniqueness is probably best understood when contrasted to crystals. I didn't get to practice with this one, so, oh, there it is. So on the left here, I have a crystal, and on the right, I have a glass, right? The beads are the same color, they're about the same density, but looking at them, you see that there's something sort of fundamentally different. Right? If I asked you to maybe name it, you'd probably come with terms like disorder or periodicity on the left. But but it may be hard to point out exactly what is it that makes this one, solid and this one solid as well, right? They seem to have no commonality here. They're both solids. And in a sense, that is the modern incarnation of the glass problem. That's a problem that we're still trying to solve today as chemical physicists. Now, to make this into more concrete sense, let's break down crystals and glasses. So how do we generate crystals? Typically, the way we generate a crystal is that we take a liquid at a reasonably high temperature and we cool it. So these are two different examples, right? So we can take water. You're familiar with water, I hope. So I live in North Carolina, so people are not as familiar with this phase transition I'm about to describe, but around here I hear it's pretty common. When you take this water below 0 Celsius, it transforms into a new magic material that's solid, right? That we call a crystal. It's ice, and it has this very nice property that you can put in your drink, and it will make it more pleasant. But if you were able to actually use that, well, we don't quite use glass to look at atoms, but we've used glass to get to be able to understand the position of atoms. What you'd see is something like what you see on the right there, on the top right, which is a nice periodic network of those water molecules, right? They're so periodic that if I give you the position of one water molecule and I tell you it's in a crystal, you can figure out the position of all other water molecules in the entire cube of ice next to it, right? So it's very profound. You need very, very little information to describe the entire material, right? Same thing if I take metal, going back to the rocks of ancient time. If I take those metals in the kiln that were accessible in antiquity, right? I would be able to get a liquid that if I cool down, there'd be also a very sharp transition where it would become solid. Right? And each metal is a different melting point, but the end product is always the same, something that's also very periodic. Where you can see on the right, this is actually transmission electron microscopy of the atoms in that lattice. So you're looking at the real position of the atoms in the metallic lattice. Right? Again, if I give you the position of one of those atoms, you can figure out all the other ones by just translating the atoms around in this sequence. Now, this is what happens to crystal formers, as you call them, but there's many liquids that when you cool them, don't actually crystallize. Right? The example, the one that's been most talked about by Kate, right, is a silicate-based glass, so silica that you extract from different sources, right? So you get something that's, we now get to be transparent. We know it was not always transparent, right? But if you look at the atomic position in the top right of those atoms, it's highly disordered. Right? If I give you the position of one atom, there's many different other places where you could put the atoms next to it and reconstruct a network of that glass former. Right? And if we're willing to expand the range of the epistemological range of the word glass, right, we can even think of other liquids that, if I cool them down, will form a solid that is not crystalline and call that glass. So we can use plastics, for instance, long polymer chains that if I cool them down will form something solid that I can use also in the kitchen, right? But if I look at a microscopic version of it, it's also highly disordered, right? You have long chains that are intermingled, entangled, we say, is a more technical term. Right? And these two materials have the same property that they're both amorphous, right? They're disordered. I cannot describe their position using simple information, the position of the individual atom, without simple information, and yet they're solids. And in a sense, we can, and this is what we call glassy materials, right? They're in the vernacular, in the language that we use every day, we might not be calling the plastic a glass, but it's a glassy material nonetheless. Or you would say, maybe more generically, it's an amorphous material. But for the physicists that are trying to understand the properties of those materials, they're all under the umbrella of a glass. Now, if I were to summarize this information in a single graph, right, the glass problem, in a sense, for material scientists and for Corning in particular, or anyone who tries to make glass, right, is that you take a high-temperature liquid, where I start at the top right. I take this high-temperature liquid, and what I'm looking at here, the x-axis is temperature. So I'm cooling temperature by going to the left. And what I'm going to be monitoring, say, is the density of that glass, or the specific volume, the volume per unit of mass of that liquid. right? And if I cool it, right, that specific volume will contract, so it will get denser and denser. And there is a transition, this first sharp line, right? Most liquids, or a lot of liquids, if you were to cool them slowly, they would crystallize, and then suddenly the density would change abruptly. There's a very sharp transition from the red line to the blue line at the bottom at what's called the melting transition, so the rightmost dashed line. That would correspond to the formation of that crystal, right? So you start from a liquid that is disordered, and that becomes that very periodically ordered crystal. Now, to get a glass, somehow you need to avoid that process. You need to make sure that you don't actually crystallize, so that you can keep on cooling that liquid, and then at some point, as you cool it, it becomes more and more viscous, right? It gets to be in this viscous regime when you can deform it, and it sort of keeps a bit of memory of where it's been, and you can shape it, you can blow it, right? It's a malleable material, and that happens very, very gradually. But at some point, that malleability becomes, or the deformability becomes so small that I have a solid, become rigid. And so the key problem for material scientists in that sense is, how do I make sure that the liquid I have at a high temperature does not actually crystallize? I need to avoid crystallization at all costs to be able to obtain a glass. And the art of glassmaking from antiquity to today, right, in a material science context, is how do I come up with a nice composition of atoms or molecules such that when they come together, they don't rapidly crystallize. So that's one version of the glass problem, or yet one more version of the glass problem, I should say. Now, one thing to keep in mind that's really important when thinking about glass is that what I'm contrasting is the material on the left, right, this crystal, with the one on the right, a glass. But the glass is not just a defective crystal, right? I'm not just taking something that's nice and periodic and adding defects here and there, and I get a glass. It's something fundamentally different, right? It's based on disorder. It's not order with a bit of mistakes. It's fundamentally and fully disordered. Now, because it's a fundamentally different material than a crystal, if we want to describe it from first principles, right, which is what physicists attempt to do, right, using the fundamental relationship between atoms to find the emergent property of the material that they generate when coming together, I need a fundamental understanding of that material. So I need to understand, in other words, what are the laws of the disorder. Let me repeat this, or maybe contrast the two materials, maybe from a more mechanical, a more physical standpoint. Right? So if we were to understand solids purely on what we know about crystal order, right, about those periodic ordered objects, right, we would say that a solid is an equilibrium phase of matter. What does equilibrium phase mean? Meaning that it's a phase of matter that keeps no memory whatsoever of how I generated it. Whether I cooled that liquid quickly or slowly, it doesn't matter. Once I have my crystalline solid, it's lost all memory of where it came from. How did it form? It happened very suddenly, say at 0 Celsius, when I cool my water, it turns into ice, right? And it's a crystallization transition, which is what we say a first order, a discontinuous transition. There's a dramatic change in the property. There's a jump in the line of the specific volume at the melting. You know that the density of ice is markedly different than that of water at that same temperature at 0. So there's clearly something that's qualitatively changing discontinuously. If we think about the landscape, so if you think about how matter organizes as exploring a landscape of possible states, the crystal state would be a deep minimum, right? In which on each direction, if I want to deform it, I need to pay some energetic price. A more technical aspect of this. How do crystals flow and deform? Well, they actually deform through defects. Right? These are different examples of defects I've depicted here in this slide. Right? You can have parts of it that are crystalline, that are coming up, and matching up to other crystals, and at that plane of that boundary between two crystalline regions, that's a part of the crystal that will naturally deform as I shear my crystal. Right? A perfect crystal will have much better resistance to deformation than one that has a well-pronounced defect. That's a natural plane along which the material will break, for instance. Right? And if I look, lastly, let's say, what are the excitations around that solid? So if I take a perfect lattice, I ask, what is the, if I heat it up a bit, if I heat that crystal, I dump a bit of energy, what is the lowest energy excitation that will proceed? Reload this slide in case it appears. You can sort of see, or barely see, there's a bit of a breathing mode. This breathing mode we call the phonon, and this is how actually sound traverses a crystal. This is how the lowest energy excitation, I can talk at my piece of ice, and sound will transport through those breathing modes of it. So this is the understanding of a solid based on what a crystal would be. But if we think about glass disorder, or a glass disorder as the reference for a solid, everything's different. Right? First, a solid can be a non-equilibrium phase of matter, which means that it ages, right? It ages with time, it evolves, it remembers. That is a term that Kate used, like the material as memory of how it was prepared, because we've frozen in some of the structure that we put in. This is how we get it to be a solid, but it's not an equilibrium one. It's very highly dependent on how I prepared it. How does it form? It undergoes a glass transition, which is this smooth change in properties as the liquid becomes more and more viscous. Or what happens when I take a material and I would crunch it, I would jam it, so I can quench it quickly with temperature, or I can apply pressure and also get it to form a glass. I want to describe again the landscape of that material, right? In a crystal, it was a well-defined minimum. In a glass, it's a very, very rugged landscape. There's actually a ton of different minima that are very similar to one another, but they're all very different. That corresponds to all those possible positions that atoms can take place and still form a glass. Right? I actually have a number of minima that grows exponentially quickly with the number of atoms I have in my material. Right? The crystal had 1 ground state. Now I have a number that's of astronomical size compared to. And then I can ask the same question, right? So if my crystal was able to deform because there were defects in it, but in something that's amorphous, in something that's disordered, what is a defect? How can it be defective if everything's defective? Everything. And I can also ask, like, what are those excitations that take place in liquid? Actually, if I look at the excitations that one can get, so in a crystal, I should say, these excitations were first described in the early 1900s by Debye, right? And they correspond to this straight line here, the straight line on this plot. So this is looking at the heat capacity, how much heat the material can absorb as a function of temperature, right? So it ends up being a straight line on this plot. But if I look at a glass of the same material, right, the same atoms, but one crystalline, one amorphous, I get this shoot up that corresponds to the fact that there's many, many different excitations in a material that have nothing to do with those nice breathing mode that I depicted. Right? So trying to make sense of where those excitations come from is also sort of part of the mystery. And I sort of hinted at this problem before, but glass for physicists is more than a glass. Right? Glassiness it doesn't just belong to silicate glasses that we use to make windows or to drink water out of. It can take place in suspensions of colloids. So these are sort of micron-sized particles, about 1/100th of a human hair, say, and it's suspended. You can think of not the baby, but the sand underneath the baby as being a glass, right? So or a glassy material, and an amorphous solid, right? Because the sand on the beach, I can walk on it and I don't flow through. So clearly it's a solid. It's a solid that's obtained through jamming, and it's amorphous. So I know it's on a very, very different scale than the glass that we drink out of, but this amorphous solid property is the same. So is there some connection between this amorphous solid that I walk on the beach, or this shaving cream that I can use that it remains solid in my hand up until I shear it? Don't shear it very often. And even to push this analogy further, there's a lot of our tissues, right? This is a movie of cells in a biological tissue where the cells are not really moving either, right? There's no transport. It's a solid. It's a solid made out of cells. So can we understand the properties of that biological solid using notions from the physics of glasses, right? And actually, if you're willing to expand your mind even more, you can say, well, there's more than materials to glassiness, because we can find systems that become very sluggish, bit like the liquid that becomes a glass in mathematics. When you look at random polynomials, you can find them in computer science when you're looking at optimizations in random landscape. You can find them in biology, not just in the tissues, but in how we evolve in a complex fitness landscape of who's more adapted to the environment or not, or even how the proteins themselves fold in a very rough landscape. And all these materials are glassy, even though none of you would ever call them glasses, but we nonetheless dare use the term glassy to describe them. And this, the glass problem for physicists, right, is understanding this universality. Because if you have this universality of phenomena, it begs for a universal explanation. This is what physicists live for, like the simple explanation that can explain everything. The equations of Newton that explains why the apple falls and why the moon sticks to us and why we stick to the sun and everything else, right? A very simple equation. The same thing here, right? Can we come up with very simple descriptions that explain glassiness? Now, I'm not the first one to come up with this problem. And this is sort of a state-of-the-art article in the New York Times from about a decade ago, where Dave Waits, who's a very, very prominent physicist in the field, he was interviewed and he said, there are more theories of the glass transition than there are theorists who propose them. So we're very far from universality if not only can we not find one theory that explains all materials, but we can't even find one theory that explains one material. We have a plethora of theory to explain. It's sort of a failure of physical universality in that context. And you should know that Dave Waits is an experimentalist. This is why he likes to joke at the expense of theorists. He's a brilliant experimentalist, to his credit. One of the images I showed earlier came from his lab. So this is just funny physicists laughing at each other. Right? But actually, when I first read this article, this reminded me of a very classical text about the philosophy of science, written by Thomas Kuhn in the 60s. And it's called The Structure of Scientific Revolutions. It's a small little book. It's fairly easy to read. And he describes in this, he's trying to understand how it is that innovation appear in science. And he's describing different historical events to see how people came up with new understanding of materials. And in this case, he's describing the theory of oxidation in the 1600s and early 1700s. He describes the theories at the time as there were almost as many versions of the phlogiston theory as there were pneumatic chemists. That proliferation of versions of a theory is a very usual symptom of crisis. In a Kuhnian reading of the glass problem, at least in the last version I introduced, we would say that the glass problem has been in a state of crisis for decades now. It's a sort of uncomfortable situation. Now, Kuhn is also really, really compelling because he also tells you how it is that you get out of a crisis. Right? The solution is super simple. All you need is a paradigm shift. All you need is to change the way you think, and then the solution will emerge. Easier said than done. But what I will quickly argue in closing is that the paradigm shift has happened. And is there a pen somewhere I can correct this slide? This is something I missed. So what should appear in the caption at the top is D goes to infinity. So the paradigm shift that's happened, and it's not you would like to think that a paradigm shift is a sudden event, right? Like a landslide and everything gets reformed, but really this is a shift that's taken place itself over decades, right? Where we have finally been able to obtain a solution from first principles, like physicists love it, to the description of glasses. This is really profound. There's only one caveat, that this description is precise and exact only when the dimension of space is infinite. Now this is, I know you might be skeptical, right? But infinite looks really far from 3-dimension, right? Where most of us spend most of our times. But give me one chance, right? But if you take 1 over infinity, that's 0. And if you take 1 over 3, that's 1/3. And 1/3 is actually pretty close from 0. So maybe this definition is actually not so crazy if you accept that maybe you should be looking at 1 over d. And this is what we, believe it or not, we fundamentally believe. And what we're about to do in the spirit of a Bridges lecture, we're trying to bridge between the infinite dimensional solution and 3-dimensional glasses. And I'm part of a collaboration that's called Cracking the Glass Problem, the Simons collaboration on cracking the glass problem. I came up with a name. You can. Everyone hated it, but somehow. So we're 13 PIs, and we're working on this problem together, funded by the Simons Foundation in New York. And this is precisely what we're doing, right? I'm not lying to you. We're starting from this 1 over dimension. So this 0, this is infinite. This is what we know. And this is where we want to get, 1 over 3. And we're building the tools, building the understanding. And it looks like there's a good chance that before the money runs out, we will actually have cracked the glass problem. At least the last version we could come up
Thank you, Patrick. Thank you, Kate, for this exploration of glass from an historical and physical perspective. Too bad we didn't mention liquid crystals and all of that. Entirely different thing. Before we move ahead to question and answer, so you will have an opportunity to ask questions to our distinguished lecturers. I am supposed to remind you of the following lectures that will be taking place at St. Jerome's in November. The next lecture in the St. Jerome University Lectures in Catholic Experience takes place on Friday, November 15th. It's entitled A Paradox of Pleasure, Jean Vanier and the Growth of L'Arche. It's presented by Carol Whitney Brown, author of Sharing Life, Stories of L'Arche Founders. The reading series continues on Friday, November 22nd with author Deanna Young, who has been nominated for numerous awards, has written 4 books of poetry. And finally, the next lecture in the Bridges lecture series will take place on Friday, November the 8th, and will include world-renowned zombie scholar, Dr. Arnold Blumberg, and Professor Robert Smith, the professor of disease modeling from the University of Ottawa. So don't miss this one. For details about upcoming lectures and all the series that take place at St. Jerome's University, please visit www.sju.ca. Now, I will invite our 2 lecturers to come and join me, and we will be opening the floor for questions. And before we start, we have some microphones that will be moving around the audience, so please wait till a microphone reaches you before you ask your question so that it can be recorded. And off we go. Questions? Yes, sir. Whoa, wait. Microphone.
Rule number 1.
There you go.
I've heard of supercool fluids and things like that, and that it's possible to sort of the equivalent to supersaturated, it's possible to take them down in a certain way and keep them from crystallizing. But I don't, what's the end state of that when you finally do that? Do they hit something then and zing, they instantly crystallize, or what?
So it depends on liquid. There's some liquids that you can, water is a classical example. You can cool it, you can super cool it for tens of degrees, especially if you're, this is an experiment that you can see on YouTube or do at home. right? You can take a water bottle, very clean, and put it in the freezer, minus 18 Celsius freezer. It will remain liquid, but then if you shake the bottle, it will suddenly front that propagates crystallization of the system. So this is one of the possible ultimate fates. But if you are a brilliant antiquity kiln producer, you might be able to find the right mixture of atoms and additives such that this process does not take place on any relevant timescale for lives.
What if you shake really hard?
I mean, it's a real question, right? In between the liquids that easily crystallize and those that won't crystallize on any relevant timescale, there's everything in between. So there are some liquids that, if you do shake them, you will manage to form a crystal, and if you don't, if you just keep on cooling them, they will become a glass. Right? And so the ultimate fate of those that don't actually crystallize is that they become so viscous that they stop moving on any relevant human timescale. So if you and I lived for 15 billion years, then maybe we would see them flow, or maybe 250 billion years would see them flow. But on any relevant timescale for the materials or for our lives, they will.
Okay. Yes.
By just looking at it, how do you know if a material is crystal or glass?
What sort of eyes do you have?
Well, that's kind of the rub, right? Is you don't just by looking at it. So that's why I think glass is really tricky, because you can't identify. That's why, right, that head of Augustus that I talked about, people thought it was glass. I mean, we have this problem all the time, like when we find like little bits and pieces of things in archaeological context, and we're kind of like, well, what makes it look like glass, right? How do we define glass? Like, as a human being, person in the world with normal eyes, you have a kind of range of what you think glass is, and you look at it, and then you talk to a person like Patrick, and he thinks about it completely differently, and like he needs to look at it on that microscopic scale to be able to define it. So I think
So I was going to punt
yeah.
it back to you, right?
Yeah.
In the field, when you find a piece, you don't
Yeah.
know, so you send it to a lab and someone tell you it's
yeah, or
glassy
you
it's
don't,
crystalline.
and you kind of are like, well, how much, like, is it friable? Does it break up? But maybe it's just really badly weathered. I mean, we miscategorize, like, and that's what you can't even trust publications sometimes when they say, we found glass, and you're like, but did you really find glass? Or do you just find something that's kind of shiny and vitreous looking and looks like what you think might be glass, but that, yeah, I mean, you've hit the nail on the head, is that it's hard to do.
So my question was actually a genuine one, because if you use light that comes from those lamps, the ones that you can actually perceive with your eyes, the size of the wavelengths are, what do we say, hundreds of nanometers, say 1 micron. Half of 1 micron. 1 micron is 1/millionth of a meter. But on the scale of the atoms, this is still ginormous, because the atoms are 1,000 to 1,000 times smaller than. So as the wave hit the material, they can't sense the fine structure as to whether something is periodically ordered or amorphous. But if you use X-rays, X-rays are about, these are also wavelengths, they're also waves, but the size of the wavelength is much more comparable to that of atoms. Then how that light interacts with the material will be very different depending on whether it's crystalline or amorphous. So this is typically what you need to do. To probe something that's very small, you need something that's about the same size, able to see the difference between one.
I'm going to exercise chair's privilege in suggesting an experiment you can do at home. If you have an old pair of polarized sunglasses, take them apart and bring the two glasses together and rotate them until you can't see. And then put something that's crystalline in between, you'll see it. But if you put something that's glassy in between, you won't. It's called birefringence. Try that at home.
Good.
Just find really old.
Really old. But they have to be polarized. Next question. Yes, sir.
What about Seaglass?
So Seaglass, like you're talking about the kind of like little pieces of things. So what that is it's usually just old bottles and other pieces of broken glass that have been tumbled in the ocean. So they get really like soft edges and they don't look like broken pieces of bottles anymore because they've been worn away. So you find different colors. You find that like blue, you find that green. Those are all pieces of old, that's basically what you're taking away stuff from future archaeologists to find, right? You're like doing, but it's man-made, it's human glass that's the ocean's worn up and worn away.
Wouldn't it be more like the hard that you're trying to explain the glass problem after it's been through the salt cycle, and so would it affect the glass problem?
Well, but it doesn't affect that molecular structure of glass, right? It only affects that visible appearance. Just like that weathering problem, remember I showed that pendant that kind of had that chalky, dusty appearance? That doesn't change that physical structure of glass because you haven't heated it up and cooled it back down, right? Am I? Yeah.
Yep.
So
She's right.
it's still glass. It's still that solid state of that non-crystalline structure. It's just that surface that's kind of worn away.
No, if you break a kitchen glass, it's still glass.
Yeah.
It's just not a kitchen glass.
Yeah.
You two are coming to Science Open House tomorrow, right? Should. Oh, there's a question way back there.
This on? Now it is. I'm aware that glass in old houses and places like Schneider House and so on is noticeably thicker at the bottom than it is at the top because it has flowed, I've been told. My question is, does modern glass do that as well?
Yes.
Can we expect our skyscrapers to sag?
So I almost jumped in when Patrick was talking about that flow, like this time span of flow, to say, and actually, because it's actually a common like a misconception out there that those window, like the medieval glasses and everything, they are in fact thicker at the bottom than they are at the top. Well, it's not because they've flowed over X amount of time. It's because when they were installed, they were thicker at the bottom than they were at the top. And it has to do with the way they're making those glasses. So they're using, it's called this crown glass method, and it's, anyway. But it's an uneven thickness of glass that they're installing in the beginning. So they were smart about it, and they're like, well, let's put the heavy part, the thicker part, at the bottom so that it's a little bit more stable. So they've always been like that. So yeah, we're safe, I think.
Yes, sir.
Someone will get
When they first started blowing glass, how did they blow? I've seen it a thing at the Corning Museum when they have this long metal tube.
Yep.
But they wouldn't have had a long metal tube.
Well, they did. So the Jerusalem glassblowers were doing something really unique that we haven't seen anywhere else. So they were actually blowing glass from glass tubes. So, and we've got a video on our website that and you can find it, I think, on YouTube, that shows what this would have looked like. One of our glassblowers doing it. So it's just it's a tube, and they were using glass tubes. They're folded pieces of glass, and they're using them to cut into sections, make beads, other things. And we think it might have actually been by, not necessarily an accident, but by heating the end of that tube, then you get a closed tube and you blow into the end of it and you suddenly end up with a bubble, and then it's finding out the application for that bubble that turns into glass blowing. But there's, not very much later, the Romans were pretty sophisticated. They had iron pipes, they had iron, all kinds of, so it's not so they were using probably iron or lead blow pipes, just like our modern glass makers use.
Once again.
You were talking about the difference between glass and crystal and how they were formed. If you took water and you put it in the refrigerator, would there be a state where you could take it out, shape it, and put it back and it'll be glass?
I'll let you
Wow.
I'll let you take this one.
Yeah, I'll take it. Thank you. I'll rephrase your question. You're asking, in a sense, can I form a glass out of water, a glassy material out of water? 'Cause, you know, and the problem with water is that it crystallizes so easily that you actually, it forms a crystal before, even if you keep it very pure and even if you don't touch it, it will form a crystal sort of spontaneously around -40 Celsius. You can say, well, okay, but what if you cool it really quickly? Well, even if you cool it really quickly, you can't dissipate the heat fast enough from the boundaries to be able to keep it. Now, the way people manage to get amorphous ice is that they put it in very, very small cavities in a porous rock. Then you can, if the size of the cavities are small enough, you can get the ice to remain disordered and amorphous, but never to the point where you never have enough that you could blow it or shape it, because you have to do this on a human scale while its pores are.
Then what type of liquid can you make like a glassy material out of?
What kind of liquid?
Yeah,
A lot. You can take, there's some metals that you can.
but like some kind of liquid that you might see in your everyday life.
I mean,
I got one.
yes, okay.
Yeah, I got one.
Thank you.
You can actually, I think, I was gonna say don't quote me on this, but I'm being recorded, so it'll. What I'm told, like that our glass makers will do sometimes to demonstrate this, is actually use sponge sugar. So you can blow sugar. You can blow sugar like you can blow glass.
Right.
And actually, the art of confectionery, right,
Yeah,
the art of
yeah,
making
right.
candy,
Right.
if you want candy that are transparent, this is the glassy form of sugar. Right? Those white sugar cubes, because they're crystalline, they diffract light. Great suggestion, thank you.
Okay.
Awesome. Oh, yes, right there.
So I'm just kind of curious, like now kind of confining the scope as like the glass, not like the glassy objects. So within glass, like some glasses like perform differently from others. Per se, some certain types of glasses is more whether depends on the situation, but some are more bearable than others. But like if they're all amorphous, then what are the properties that we're looking at that makes them like different from each other?
It's a very great question. And it goes back to the slide I had when I was showing that glasses have a memory of how they were prepared. Right? So depending on how you prepare the glass, you will get glasses of different properties. You've probably seen tempered glasses on some contexts. Somehow they feel that they're more robust, or they have different breaking properties. So there's different cooling and heating mechanisms that you can make your glass go through, or protocols that will give materials with different properties. And this is where all the material science and the engineering of making new glasses that like Corning would do is in mastering those properties. What does it mean microscopically? Because you said they're all amorphous. Well, it's because not everything that's disordered is exactly the same. Things can be disordered in very subtle ways. Now, I can't go and tell you, well, you just need to measure. So that's a real problem, right, in science or in the physics of glasses. Like, what is the quantity I could go and measure when I look at the atomic positions and determine whether something is a glass of a given type or a glass of another type? And there are some answers out there, but to a large extent, it's an open question.
Can I just add on a bit? Just wondering. So per se, of course, we cannot control all the parameters, but then are there some kind of like specific spots so we can be looking at? Per se, now we have like 10 materials, and 8 out of 10 perform a certain physical property, and then we can kind of summarize as like they all share some kind of similarities.
So are there trends, for
Yeah.
instance, right? Yeah, so if you more slowly anneal your liquid, so if you cool it more slowly, as long as it doesn't crystallize, but then you'll have a glass that is that is more resistant. A quickly annealed glass will be more fragile to deformation, will break more easily. So that's one trend. There's many such trends, right? This is why there's large glass makers in the world that will be documenting, if I add a little more of this additive, if I cool it a bit faster, a bit slower, and you can sort of parameterize all this phase space, and you get those trends. I showed you so the low temperature excitations. So those low temperature excitations are also much more prevalent in quickly annealed glasses than in slowly annealed ones. So slowly cooled. And there's many more such things, right? So yes, there are many things we know, but a lot of it is sort of a ad hoc. We know because we've done it, but we don't necessarily have a good first principle understanding as to why that is, except in infinite dimension.
My father was a storeman in a glass factory, triplex glass, in the UK, just at the outbreak of the Second World War. And he was called up to the top office one day with a sample of glass to demonstrate this to some people from the army, because they wanted armored glass for the tanks and so on. And to demonstrate how good the glass was, the chairman of the company took this lump of glass and threw it out of the window onto a cobbled courtyard, and it went clang and it bounced. And there were two workmen down there painting a window or something, and one of them says, "Hey, Fred, look at that. Isn't that fantastic?" And he picked up the piece of glass and he tossed it up in the air again, and it came down and it smashed into pieces. What property explains that?
Luck.
It's a great question. Next. This is the magic of your phones and the Gorilla Glass, right? This is so there's lots of engineering and material science that goes into this, and unfortunately I don't know the answer to this specific one. But I mean, why does your windshield, when you hit an object, will scatter in all those little pieces, while a glass that you drop in your sink scatters and breaks apart in completely different ways, right? This is the magic of how malleable, in the sense that what you're demonstrating or what you're illustrating is how important and useful this material is, because there's so many ways in which you can tune its breaking properties as well, which you wouldn't be able to do with a crystal, because all crystals are the same. But this specific one, I have to pass.
Sir, over here.
As I understand it, when pane glass breaks, it has a common break pattern in the shards and common. What causes that, and is there anything that can affect that or change it? I know that that's actually something that they use in forensics and insurance, because people will try to fake a break and enter. They don't want the glass on the inside of the house, so they'll break it from the inside, and more of the glass will, I think actually more of the glass goes on the inside than on the outside, and it's due to the break pattern, and they can actually tell which way it was broken or which direction it was broken in.
Me again? Okay. The answer is the same, actually. It's a really great question. But what this is illustrating essentially is that all window glass is made through roughly the same preparation protocol. Right? So the final material has reproducible properties such that you can use it in a forensic context. How it breaks will break in exactly the same way that the window from your car breaks on your windshield breaks completely differently, but always the same, right? And yet it's roughly the same ingredients. It's an amorphous silicate-based material, but that you're able to really fine-tune its properties, not just its translucency, which is what Kate mostly emphasized on, but also how it breaks. So you can make sure that it breaks in a way that won't endanger the people around the object when it does break, like in a windshield, or it breaks differently. The constraints on a window pane for a house are different, and this is why it breaks differently, or it's been designed to break differently. But again, I can't really tell you how it is that the stress that propagates through this particular window would. I can give you the name of someone who would know.
But is there also how the glass is processed? So if it's stretched in one particular direction, for example?
How it's strained, how it's cooled, how the precise composition, all of this come into play. And some companies make billions out of figuring this out.
I only deal with it after it's broken. Usually.
Young man over there.
Something that you mentioned earlier is how impurities in glass can give it a blue or green tinge. What sort of chemicals would cause those impurities?
Usually it's iron. But there's also whatever other things are mixed up in the sand that you're using. So iron, copper, those are the most common ones. Do you know any other? Or what are
So the
usually-
red, so if you think about the stained glass, right, what are the different
Sure.
additives that people would add?
Oh, well, what color? So if you're intentionally coloring it, so if you're talking about like a really vivid colored glass, then you add things like cobalt and, manganese, antimony. Those all give glass a distinct color. But the things that make it kind of that usual color, like it's, again, it cakes on different properties based on what is in it. There's all kinds of different things. And the other thing about this is what's tricky is that just putting in something like copper into a glass doesn't always make it turn one color. You have to do, it's not like a one-to-one equation, and that's why glass is such a fun material again, that you've put copper in, and then you have to treat that glass in a really certain particular way to make that copper either be a blue glass or a red glass. So it's different, it's not just kind of adding one ingredient and making it turn a separate color. You have to treat the glass in different ways.
The general answer is you add different trace of metals, and the metals will give a different color depending on their excitation states or their oxidation states.
Anyway. Microphone.
So I feel like when I was in school, I learned that everything we knew about, like, solids are understood and liquid is understood and gas is understood. And now you're telling us that, in fact, we don't understand glass. So I just wonder, what else we don't understand? Is science and engineering is engineering so far ahead that there's a lot of science we don't understand?
It's a great question, Benoit.
We'd be out of a job
Got you
if
on the
everything
hot
was
seat.
understood. You understand that.
So just one small detail. When they told you in high school that solids were understood, they really only meant crystalline solids.
Yep.
And if you open a textbook of solid state physics, 99% of the textbook is going to be about crystalline solids because we understand so much. They would talk very little about glasses. Is there a lot we don't understand about materials? Absolutely. Right? What's special in a sense about glasses is that it's such a ubiquitous material. It's so close to us, and yet some very fundamental aspects of how they obtain their properties remain. There's lots of exotic materials out there that we don't understand, but they're not as immediate in our daily lives as glasses
Yeah. Sir, back there. Oh, hang on. Microphone's coming.
This has to do with the colors again, coming back to lapis lazuli and colors. And I've heard that one of the challenges that are going to be facing the reconstruction of the Notre Dame Cathedral in Paris and the structural fire that occurred there, as well as in Chartres, in the cathedral in Chartres, that the color blue, that they still have no one has yet to figure out how those medieval craftsmen got that color. Is there any truth to that, or is that
In the glass
a medieval myth?
specifically?
In the color blue in the stained
Yeah.
glass windows, that they still don't know how they created that that color?
So for that specifically, I don't know if that's true or not. It's a little bit outside my field. It's a little bit late.
But you know someone who does.
Yeah, I can find somebody who does. But I think but the broader question you're asking is that we do still have a lot of mysteries about the way they're making, because we have to reverse engineer everything. So it's pretty rare that we actually have texts or recipes or anything like that, even from 100 years ago. I know a lot of people, or I know some people who are trying to figure out how Carter Steuben was making their glass and what chemical compounds they were using to do that. And those we have recipe books for. So we have to look at the only method we have is to do the scientific analysis and look at what basically the chemical composition of a glass is. And then we have to kind of think about what chemicals are coming in together and what's in the base sand that they're using. So we might, and sometimes we can identify sources of those materials and sometimes we can't.
What the
Yeah.
craftsman space looked like, also the preparation, what the tools they had at their
Right,
disposal.
right, exactly. And what are they, we might find cobalt in the glass, but what's the cobalt source? What kind of mineral is it coming in with? So I wouldn't be surprised if that was in fact the case, that they don't know exactly how it was made. We can replicate the effects of it, but we can't replicate exactly what they did to create it.
Yes.
So I can definitely appreciate why you would like to have a unifying theory just for the pure theoretical purpose. But I'm just curious, it seems like people are able to do a lot of interesting things with glass already with our minimal knowledge. Is there some kind of dream in your head where if we could just do this with glass and we have to understand it better to do it? Is there a dream for some practical application of that theory?
Often when we develop a theory in this context, we don't really know what we're going to learn from it. We're already, in a sense, making sense of certain properties, and we've been able to, so more in the theoretical world, we've been able to improve algorithms on when you simulate glasses based on our understanding of a theory. Now, those algorithms are not available to craftsmen who prepare glasses, but yeah, I mean, whenever you get a theory that can describe a material, you can then hope to reverse engineer or to optimize a material with respect to certain properties using this expression, right? Using this construct. So that's one improved design that you could always hope to be able to do more. But honestly, we don't know. And it's possible, and others have said this before me, that it's possible that actually what we learn about glasses doesn't help us make better glasses, but they might help us design better algorithms for solving complex problems that computers cannot solve today. It's possible that and it has already in some ways, right? Some interesting historical path of the development of a theory. So yes, we're in this because we think that the problem is so generic, and what we're going to learn from solving this problem will teach us a lot of things about solving other problems that maybe we don't even see how they're related, but once we formalize it, we see that connection.
Thank you.
And maybe we'll do better classes.
And that's how great discoveries happen. You try to solve a problem and you stumble on something else. Other questions? Oh, yes.
So you can make a crystal by heating something and cooling it, right? So if you take pure carbon, can you heat it and cool it and it turns into a diamond?
So the specific case of carbon, when you heat it, one of the common problems is that you do this in presence of oxygen, and it will chemically react and make a fire. So that's not reversible, and so you can't just cool it down. A lot of the minerals like carbon or like diamond you're describing is not just happening upon cooling of liquid carbon in absence of oxygen. It's actually happening through very intense pressure. So the gigapascal scale or of applied pressure that will be able to transform the graphite into its then free energy minimum, or its optimum structure, which is diamond. What's peculiar about diamond is that once you remove this pressure, it doesn't quite flip back to graphite. This is how the jewel industry makes a lot of money. But it's this process actually would normally take place, but it's a very, 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 very slow one. So that's why you inherit diamonds.
But could you make carbon into a glassy material?
Good question. I mean, it tends to form, so the chemical drive to form sheets in carbon is really, really strong. So you tend more to form those sheets or have them wrap up or form buckyballs or carbon nanotubes with much more ease than you can keep it amorphous. So that's my quick answer. Should.
Sir.
I just have one historical question, which is, so from people asking about additives and things, I was just thinking the technical advances in making glass over time, have they been driven more by people who were lucky enough to be located next to the right stuff, or was that more just driven by advances in people thinking of new ways to deal with sand or whatever that they?
Yeah, I think that's a really interesting question. I focus and we talk a lot about kind of the history of glass in Egypt and Syro-Palestine and these very traditional glass producing regions throughout antiquity. And we do tend to see they have really good ingredients to make glass in that area. So it does seem to make sense that that's where all this kind of nexus of this innovation, because raw ingredient, it's cheaper. You've got the stuff right there. You don't have to ship it from super far away. But it is a pretty, there's only so much I can talk about in 25 minutes or so. But there are certainly individual glass industries that are emerged independently in other parts of the world. So medieval Europe, they're using local sands there to make glass. There's a lot of, it's partially a question of how much you have to process your ingredients. So most sand is pretty silica rich, and you can therefore make glass from it. But it's a question of how many other contaminants and how much other stuff you have to do to make a really good glass from it. So that's why they're importing ingredients as they can. But you can work on it from other, and we see plenty of innovations happening in other areas as well. But it does seem to be that, it helps to be located near resources.
It helps make the experiments possible as well.
Right.
And I think with my limited understanding of materials history, right, but it's only really starting in the 19th century that you have massive transport of materials. So you would designing, trying to get certain materials properties by blending in. Otherwise, you'd prepare the object locally where the materials are available, where you can experiment with them, where you can get a steady supply for cheap, and then export the final product. And then the desire to make where the plant is situated. So Corning's plant in Corning, New York is not there because there's a great supply of, or is it?
But that raises an interesting question, because this is actually the secret of glass. Well, a secret of glass. So it's not that Corning is located in Corning because of local sand sources. You can at that point you can bring in this glass from elsewhere. Corning is partly located where it was because it's close to fuel sources. Fuel in glass making is really, really important. I haven't talked about that, but that's what you need to do to move this material through all these heating transitions is have a good source of fuel nearby. And also transportation. So you need to be able to get your materials and products from where you're making them to where your markets that you're selling them.
Okay, I will allow one more questions because we do have a reception awaiting us. And I think that we can continue those conversations over drinks and food. So, last question? Hang on. You had your hand up before, so you'll have the last question. Where's the microphone? Right there.
Okay, again, I'm kind of curious on the part how you came up with the solution that kind of solved the glass problem to the infinite dimensions. Because normally, from a physics, historical point of view, it's kind of we kind of see stuff from day-to-day life, and then we try to generalize it, and then we bring it to an abstract level, and then we kind of along the way we have some deeper understanding, and then we go from there. But then how from this specific problem you go from the other end?
Yes, it's a very good question, and then the real answer is very long. So so I'll give a very brief overview. which is essentially in 1979 came up. A man called Giorgio Parisi came up with a new way to understand how symmetry can be broken in matter. Described the replica symmetry breaking. And if you fast forward 40 years later, someone called Francesco Zamponi figured out how to use this to describe simple liquids and their glass. This technique and all the advances that were made to describe the properties of liquids in the high dimensional limit. And this is sort of the work that he started in 2005. And I've been collaborating with him, but he's mostly been driven for the last 15 years. So it took many, many people's, sometimes microscopic contributions that build up to an edifice where you could solve this. And the method that was invented by Parisi in 1979 is now the one that's being used to understand algorithms, optimization algorithms, to understand machine learning, to understand a variety of other problems. And that's, in a sense, that is the unifying trend that also exists, that allows us to relate glasses across disciplines and across materials.
Great. So you have been a really engaged audience. Great questions tonight. I think this was just a wonderful discussion. So please join me in thanking Kate and Patrick for just a wonderful